today on Duncan Gregory, the Calculus of Operations, and the Cambridge Mathematical Journal. Duncan Gregory is recognized as a central figure in the development of the British approach to algebra during the 19th century. Along with a group of British mathematicians, including George Peacock, Augustus de Morgan, and George Boole, Gregory questioned the foundations, examined the general laws, and pushed at the boundaries of the then existing conceptions of algebra. Studies by Elaine Koppelman and Pat Allaire have convincingly argued that the algebraic insights of Gregory, as well as those of other central figures in the development of the British approach to algebra, were influenced by the exposure these mathematicians had to the calculus of operations. Now, in viewing the work of these pioneers, it's important to remember that their accomplishments did not occur in a vacuum. In the case of Gregory, all but one of his collected works appeared in the Cambridge Mathematical Journal, of which he was co-founder and editor. During his editorship of the journal, from November 1837 to November 1843, Gregory not only became the most active contributor, but he also spawned a conversation about the calculus of operations. In this discussion, young mathematicians, many of them first-time researchers, explored the method, responded to Gregory, built on his articles, and affected Gregory's own views of his work. The mathematical activity occurring in the Cambridge Mathematical Journal prompted Augustus de Morgan, professor of mathematics at University College London, to make the following comment in 1845 to John Herschel. "You should not forget the Cambridge Mathematical Journal. It is done by the younger men. It is very full of original contributions. It is, as is natural in the doings of young mathematicians, very full of symbols." Today, I'd like to explore the discussion between Gregory and the other young British mathematicians on the calculus of operations, as well as the publication venue in which this discussion occurred. An examination of this discussion gives us an intriguing window into the evolution of a research area fundamental to the development of the British approach to algebra within a nascent form of mathematical communication for young British researchers. So at the beginning of our period here, from 1837 to 1843, what were the publication options for British mathematicians, especially young, maverick British mathematicians? Well, these options were pretty limited. The transactions and proceedings of British scientific societies were certainly an option. In fact, the Royal Society of London philosophical transactions had been an option since the 17th century. For Cambridge mathematicians in particular, the transactions of the Cambridge Philosophical Society had also been an option since 1821. Well, now, while these outlets were certainly open to mathematical articles, publishing in a scientific society journal at this time did have its drawbacks. For example, a mathematician wanting to publish in these journals usually had to be a member of the society or had to communicate the article through another member of the society. Now, once the author had successfully submitted the article, he risked never seeing it again. In the case of the Philosophical Society, if the referees judged that the article was not publishable, then the manuscript went into the archives and was not returned. So a mathematician overcoming all these hurdles might wait months or even years to see the article in print, and then probably it would be sandwiched between, say, an article on the anatomy of the foot and an article on the geology of southwest Wales. So without a society of their own before 1865, British mathematicians competed with scholars from other fields for publication room in the society journals. Well, another option at this time were general, independent scientific journals, such as the Philosophical Magazine. Now, these journals allowed mathematical authors to avoid these regulations and also to publish more rapidly. However, the venue was still a general scientific one. Mathematicians had to advocate for the publication of their articles to editors who were both wary of mathematics and its appeal to their readers. There were commercial, independent mathematical journals at this time, but they were usually a question and answer, enigma type journal, usually very short-lived. One notable exception was Thomas Laybourne's Mathematical Repository. This was launched in 1795. During the first decade of the 19th century, William Wallace and James Ivory made innovative contributions to the repository using continental mathematical approaches to the differential calculus. Despite these contributions, however, the repository, as you can see here, was still basically question and answer, and it dissolved by 1835, 2 years before the foundation of the Cambridge Mathematical Journal. So we've got proceedings, transactions, and commercial journals, mainly commercial general science journals. This was the publication environment in which an ambitious group of mathematically inclined Cambridge students found themselves in 1836. In December of that year, the 24-year-old Trinity College Cambridge fellow, Archibald Smith, introduced the idea of founding a mathematical journal to Duncan Gregory, also of Trinity, the month before the latter was to take his mathematical tripos examination. Now, this examination for over half of the 19th century was a mandatory hurdle for the BA degree at Cambridge, even for those students not interested in mathematical areas. A high ranking among the Wranglers, that is the highest honor bracket for the examination, provided promising positions in the university, church, and government. Smith, the senior Wrangler in 1836, seems to have left his tripos experience with a slightly bitter taste in his mouth, writing just after the examination that he had become, quote, quite tired of, I might almost say disgusted with mathematics. A year's time, however, evidently relieved Smith of his distaste for mathematics and replaced it with a desire to encourage original mathematical research. Gregory agreed to take on the establishment of the journal after the completion of his own tripos examination. He placed as fifth Wrangler, very respectable in that year of 1837, which included higher rank Wranglers such as James Joseph Sylvester and George Green. Samuel S. Greathead, the fourth Wrangler for 1835, was another Trinity Fellow and is credited along with Smith and Gregory as a co-founder of the journal. There he is right there. Greathead soon left Trinity for a career in the church, and in particular in composing music, after his marriage forced him out of the fellowship. Smith followed another popular route for high-ranking Wranglers and began a law career. These defections soon left Gregory as the driving force of the new journal. In the preface of the first number of the journal, brought out in November of 1837, Gregory outlined his goals. In this preface, Gregory pointed out that many recognize the lack of, quote, a proper channel for the publication of papers on mathematical subjects, which did not appear to be of sufficient importance to be inserted in the transactions of scientific societies. The philosophical journals were mainly devoted to physical subjects. Gregory was confident that mathematicians were already able and willing to communicate material to the journal, while, he noted, the very existence of such a work is likely to draw out others and make them direct their attention in some degree to original research. The majority of papers in the first volume were understandably provided mainly by Gregory and his co-founders. Gregory, in particular, used this venue as a means to draw out young mathematicians to conduct original research on the calculus of operations. The calculus of operations involved separating symbols of operation, for example, differentiation, from symbols of quantity. Using the general properties of algebra, the separated symbols of operation were then simplified in order to reach a simpler solution of an analytic problem or theorem. For example, the exponent on d dx, which records the number of times differentiation occurs, or the exponent on delta, which records the order of a finite difference, obey the same laws of exponentiation that govern a variable x or a function f. The analogy between exponentiation and the iteration of the derivative had been noticed as early as 1695 by Gottfried Leibniz. Since the 1770s, French mathematicians, including Joseph Lagrange, Simon Laplace, Barnabas Brizon, Joseph Fourier, Joseph Liouville, François Servois, and Augustin Cauchy, developed this analogy, applying it to differential, finite difference, and functional equations. While these mathematicians admired the methods as a tool for discovery and verification, they distrusted them as a rigorous technique of proof. These misgivings were summarized by Cauchy here, who wrote in 1843 that, nevertheless, these formulas deduced in this way from a symbolic equation should not yet be considered as rigorously established. The method by which they will be discovered is, in reality, only an inductive method. In spite of the continental distrust of the calculus of operations, the method was embraced and developed by mathematicians in Britain. As they had proven before with their adoption of the Lagrangian algebraic view of the calculus, 19th century British mathematicians had accepted and developed some products of French mathematics that the French eventually bypassed. In fact, 25 years before the foundation of the Cambridge Mathematical Journal, a group of Cambridge reformers who called themselves the Analytical Society established their own journal for the diffusion of what they saw as a radical new approach to mathematics. This approach was an algebraically based conception of the calculus that had been developed by Lagrange that emphasized series expansions instead of limits or infinitesimals. With this new conception of the calculus, the Analytical Society saw themselves as leaving behind the fluxional Newtonian notation that had been tenaciously adhered to throughout the 18th century in Britain. At the same time, the Society felt that it could connect with what they called a century of foreign improvement in the calculus. One of the Society's efforts to promote this new direction in British mathematics was a journal. The Memoirs of the Analytical Society appeared in November of 1813. This work contained 3 papers written anonymously by John Herschel and Charles Babbage. These articles featured both the calculus of operations and the solution of functional equations, topics that would later gain popularity in the Cambridge Mathematical Journal. In Cambridge and beyond, the memoirs received little notice. The high price of publishing the memoirs, as well as time constraints related to preparing for the Tripos exam, added to the difficulties of the Society. Facing the graduation of almost all of its members and with few new recruits, the Analytical Society disintegrated in 1814, and the journal only made it through 1 issue. After its demise, Babbage, Herschel, and George Peacock continued to write reform-minded publications. In 1816, the 3 mathematicians published an English translation of Lacroix's Calcul différentiel et intégral as a way to bring Lacroix's formulation of the differential calculus to Cambridge, and also as a platform to promote their own allegiance to the Lagrangian development of the calculus. In this translation, as well as a series of articles by Herschel from 1814 to 1820, the calculus of operations was a constant presence. As the Analytical Society had done over a quarter of a century earlier, Gregory, Smith, and Greathead launched a journal for the diffusion of mathematical research. Furthermore, the founders of the Cambridge Mathematical Journal, like the members of the Analytical Society, used their periodical for the publication of ideas on the calculus of operations. Unlike the memoirs, however, the journal survived well beyond its first volume, and thus became a sustained vehicle for the transmission of mathematical ideas, and in particular, ideas surrounding the calculus of operations. Now, the journal's founders wasted no time in publishing on the calculus of operations. In fact, the first such article appears just 11 pages into the first number, Samuel Greathead's On General Differentiation. It's no surprise that Greathead began the discussion. Koppelman cites his 1837 article in the Philosophical Magazine as the first British work on the calculus of operation after Herschel's work of 1820. In his journal article here, Greathead was concerned with non-integral exponents of differentiation. He cited Liouville's 1832 work on the subject and defended this work against an unfavorable analysis of it that had been given by George Peacock in 1833. Greathead wrote that, quote, "The transition from differential coefficients whose indices are positive integers to those whose indices are any whatever should be made in the same manner as the transition in algebra from symbols of quantity with positive integral indices to those with general indices." He then gave definitions here for differential coefficients with non-integral exponents that coincided with those of positive integral exponents. From these definitions, Greathead proceeded to find a formula for the alpha order derivative of x to the n, where alpha and n are unrelated. In the fifth article in the first number of the journal, Greathead's fellow founder, Gregory, published what would become a steady stream of articles on the calculus of operations. In this first article, Gregory concerned himself with the solution of linear differential equations with constant coefficients. So starting with a general linear equation with constant coefficients, as shown here, Gregory then separated the symbols of differentiation, the symbols of operation, from the symbols of quantity. Then shortening this collection here into just a function of d dx. Now, the solution of the equation then just depended on finding the inverse of f here. So these finding the inverse operation was the subject of the problem at this point. Gregory wrote that at first sight it would appear as if the principles on which this method is founded were drawn only from analogy, but a little consideration will show that this is not really the case. He showed that x is just an operation x performed on unity. X to the n is the same operation performed n times on unity, and a plus x is the operation a plus x performed on unity, and so on. Gregory here was spreading the gospel of the calculus of operations by arguing for the method's legitimacy. And it's in this way that Gregory generalized the algebraic properties involved in the method. Gregory then gave the example of the logarithm function here as an operation that does not preserve addition. As such, Gregory noted that the binomial theorem, a result from algebra, does not hold for it. The binomial theorem does, he wrote, hold for differentiation, an operation that preserves addition and obeys other general laws. Disobeyance of the laws of combination, Gregory wrote, was precisely why the solution of linear differential equations with variable coefficients was so difficult. Now notice here that Gregory signed his article Gamma. The practice of using pseudonyms to sign scientific journal articles had been common during the 18th century and was carried into the early 19th century. Anonymity allowed a contributor to avoid criticism, and in the case of the Cambridge Mathematical Journal, it hid the fact that the majority of the articles in the first volume were written by the co-founders. Throughout Volume 1, under his own name and under a variety of pseudonyms, Gregory continued in his efforts to promote the calculus of operations. His promotional tactics took several forms, one of which was an appeal for the method's applicability. In 2 articles from the first volume, Gregory applied the calculus of operations to questions on the motion of heat. He pointed out that Fourier had used the calculus of operations for partial differential equations in 1822, but that, quote, he appears to have had some unwillingness to give himself up to it entirely as a guide in his investigations, as if he were not familiar with the principles on which it is founded. Furthermore, he noted that, quote, other French writers seem to have avoided carefully entering at all on the track on which Fourier opened. Great heed, Gregory noted, had not avoided this path, and neither had he. Gregory then went on to give examples of the use of the calculus of operations for the solution of partial differential equations, and in particular to those found in the study of the motion of heat in a ring. Another first volume article on the integration of simultaneous differential equations, Gregory used the calculus of operation for solving systems of differential equations. He explained that, quote, we have only to separate the symbol of differentiation from its subject and then proceed to eliminate one of the variables between the given equations, exactly as if the symbol of differentiation were an ordinary coefficient. Thus, the difficulty of elimination becomes reduced to that between ordinary and algebraical equations. After giving his readers the rudiments of this application, Gregory often almost gives a primer to this type of method. He used it to solve a system of equations given by the Astronomer Royal, George Airy, for a problem in mathematical astronomy. Gregory's confidence in the method and his zealous desire to promote it shines through his closing remarks to the article. We have now given a sufficient number of examples to enable the student to understand thoroughly the method, and we think that they show clearly the advantages of a process which, to some persons, namely him, might appear to carry out to a startling extent the principles on which it is founded. A further application of the use of calculus of operations in solving systems of differential equations occurred in 2 articles in the second volume on the sympathy of pendulums and on the motion of a pendulum when its point of suspension is disturbed. Now, interestingly, look at the signature on this article here. It's DGS. Now, in the second edition of the first volume, brought out by William Thompson, who would later take over the journal, these pseudonyms were identified as much as they could be. And DGS was identified as Duncan Gregory and Archibald Smith, making this a very early example of a jointly written and published paper in Britain in mathematics. The second article in this series is signed GS here. That's attributed only to Smith, although the G leads us to believe that Gregory at least had some type of influence on it. While publishing these articles that use the calculus of operations in applied mathematics, Gregory was at the same time arguing that the method could be a useful theoretical tool in pure mathematics. In the article on the impossible logarithms of quantities appearing in February 1839, Gregory gave an outline of a paper on the true nature of algebra that he presented to the Royal Society of Edinburgh on May 7, 1838, the only article in Gregory's collected works that did not first appear in the Cambridge Mathematical Journal. The true algebra, Gregory contended, quote, is the science of symbols, defined not by their nature, but by the laws of combination to which they are subject. Specifically, he discussed how this viewpoint could, quote, clear up several disputed points in algebra, such as uncertainties about the logarithms of negative numbers. To this end, Gregory carefully laid down the laws of combination governing the operation of taking the logarithm, as well as those governing the operation of addition. The operation denoted by plus, Gregory wrote, must not be considered as, quote, merely an affectation of other symbols, which we call symbols of quantity, but as a distinct operation possessing certain properties peculiar to itself and subject, like the more ordinary symbols, to be acted on by any other operation. An understanding of these laws of operation, in turn, clarifies certain analytical anomalies which do not at first sight appear to be connected. Now, while an operational point of view could clear up difficulties in algebra, Gregory argued that its generality could provide a single foundation for the proof of theorems in different mathematical fields. In this, yet another first volume article in the journal, Gregory argued that the more important of the theorems of differential calculus and the calculus of finite differences, which, depending on one common principle, can be proved by the method of separation of symbols. That's the calculus of operations. Gregory noted as an example that the binomial theorem governing the series expansion of a plus b to the n is valid for all operations a, b, and n that obey the commutative, distributive, and index laws. Gregory closed this article by acknowledging that he had overlooked Herschel's earlier work in the area and had only given credit to Brizon. This correction afforded Gregory yet another venue to promote his method. He wrote that it is much to be regretted that neither Sir John Herschel himself nor any other person followed up this method, which is calculated to be of so much use in the higher analysis. Perhaps this may have arisen from the theory of the method not having been properly laid down, so that a certain degree of doubt existed as to the correctness of the principle. I trust, however, that the various developments which I have given in several articles in this journal of the principles of the method, as well as proofs of its utility, are sufficient for removing all doubts on this head, and that it will now be regarded as a powerful instrument in the hands of mathematicians. Now, the fact that Gregory publicized the calculus of operation by giving proofs of its utility in both pure and applied mathematics underlies the Cambridge mathematical environment at the time. While Cambridge, during the first third of the 19th century, witnessed the infiltration of Lagrangian methods of analysis into its mathematics curriculum, it nonetheless remained a bastion of applied or mixed mathematics, as it was called. Both the mathematical tripos and the Smith's Prize examination encouraged generation after generation of Cambridge students to study mixed mathematics. Thus, Gregory's pursuit and promotion of a mathematical program that emphasized generality and abstraction was done within an environment highly attuned to the utility of mathematics. Moreover, the appeal of the utility of the calculus of operations, perhaps more than any argument for its legitimacy, encouraged the readers of the Cambridge Mathematical Journal to implement the method in their own research. They used it because it worked. So far now, we have seen the co-founders of the journal, and especially Gregory, vigorously promoting the calculus of operations through teaching the method to the readers, attempting to legitimize it, and demonstrating its utility. So now we come to the point where we ask, what came of these efforts? As the next few examples will show, young mathematicians from Cambridge and beyond soon joined in on the discussion in the journal surrounding the calculus of operations. One of these mathematicians was Alexander Crawford, the 15th wrangler in Gregory's Tripos year of 1837. Crawford's article on a method of algebraic elimination appeared at the end of the journal's second volume. In this contribution, Crawford gave the rules for his, quote, much more simple and satisfactory method of elimination for systems of algebraic as well as differential equations of all orders and degrees. Crawford believed that his method placed the problem of elimination in, quote, a simple and luminous point of view in which different cases treated are referred to on common principle. In his postscript, Crawford wrote that the motivation for his method came from reading Gregory's Volume 1 article on the solution of simultaneous differential equations. Appraising the method of elimination used there as, quote, more natural and properly applicable than the usual method of elimination for algebraic equations, Crawford explained that the question was thus raised whether a method similar to that in treating differential equations might not be discovered for algebraic. The question being once asked, the answer to it was soon found, especially as the paper which had suggested these reflections pointed out an analogy between the processes of differentiation and multiplication. The postscript here demonstrates that the journal was reaching readers and inspiring them to enter into mathematical discussions in print. Now, we can thank James Joseph Sylvester for this postscript. Crawford authored it to acknowledge that Sylvester had beaten him to the punch. In fact, in the issue for February 1841, the same month in which Crawford originally submitted the article, Sylvester published an article in that issue in which he, in Crawford's words, quote, not only anticipated me in the fundamental idea, but likewise devised some very ingenious rules for the more expeditious and even merely mechanical application of it. The similarities between algebraic and differential equations were also explored by Robert Leslie Ellis in the journal. The senior wrangler for 1840 and fellow of Trinity College, Ellis was second only to Gregory in the number of contributions he made to the journal. Ellis made 22 and Gregory made 26. To the third volume of the journal, Ellis submitted an article, Remarks on the Distinction between Algebraical and Functional Equations. In it, Ellis examined the relationship between algebraic and functional equations in what he says was a more general manner than earlier such examinations. He wrote that algebra, or, quote, the science of symbols, is conversant with operations and not with quantities. Equations are collections of operations equated to the symbol 0. Moreover, he argued, if one symbol is said to be a function of the other, it is, in reality, the result of an operation performed upon it. Thus, the idea of functional dependence pervades the whole science of symbols. With these principles in mind, Ellis outlined a classification symbol for equations based on the nature of their operations and the order in which they appear. For example, equation number 1 here, we have the bases A and B, i.e., those things on which the operations are performed, together with an unknown operation, x, and algebraic operations. In equation number 2, the base is x, the operations are an unknown one, y, a function of x, the operation d dx, and algebraic operations. Equation number 2, Ellis argued, because of the presence of d dx, is called a differential equation. Equations 1 and 2 are, quote, discriminated by the nature of the operations. But for both equations, the unknown operation is performed immediately on the bases. This is not so in equation number 3, where the unknown operation phi is performed on, quote, the result of a previous operation. This previous operation could also be an unknown, as it is in equation number 4. Also, the operation d dx could intervene between the unknown operations, as it is in number 5. In 3, 4, and 5, the cohesive classification principle for Ellis is that the unknown operation is not performed directly on the base. Thus, 3, 4, and 5 are called functional equations, number 3 of the first order, number 4 of the second order, and number 5 a differential functional equations. Functional notation does not make an equation functional, as equations number 1 and number 2 up here can be written down here with functional garb. Ellis writes that the name of functional equation is not happy. It refers to the notation and not to the essence of the thing. Ellis evaluated his article as, quote, the outline of a natural arrangement of the science of symbols. Now, as with Gregory, utility is still a point that Ellis felt he needed to address. He wrote that, quote, "It's not difficult to overrate the importance of a mere classification, but I hope to be able to show that the considerations now suggested are not without some degree of utility." 100 pages later in the journal, Gregory applauded Ellis's work, judged it as not only correct, but of very great importance for the proper understanding of the higher departments of analysis, and replied to it in this article. He believed that Ellis made a very good point that in this classification, the difficulties of the different type of equations are very different in kind from that which we meet in trying to solve an equation in which the unknown operation is performed on that which is known, that is a functional equation. So the difficulties were very different in the levels of classification that Ellis had outlined. He pointed out that with this functional equation, where the object is to determine the form of phi, we cannot write phi of ax minus x because phi is the unknown. We can't assume it to be subject to the distributive law. Neither can we take out the a because we can't assume that a and phi are commutative. Gregory and Ellis disseminated their mathematical ideas not only through their articles in the journal, but also as moderators of the mathematical tripos. The design and management of the tripos came from within the colleges of Cambridge, with junior fellows being appointed as examiners and moderators for short rotational periods. Moderators set the problem papers, and examiners helped give and grade the examination. This system allowed, for example, George Peacock, the tripos moderator for 1817, 1819, and 1821, to introduce questions on Lagrange's algebraic formulation of the differential calculus that had been advocated by his fellow members of the Analytical Society. Gregory served as moderator in 1841. Ellis served in these roles in 1844 and 1845, respectively. In a letter to Gregory after the 1841 tripos, starting here, Ellis indicated the power of the position of moderator, the power this position had over the mathematical directions taken by Cambridge students. He wrote that, "I can imagine the Johnians read the journal diligently. It must have done them good. But I was pleased to see how fairly your problem paper you kept clear of the parts of analysis to which your own taste inclined you most, especially as I had heard it surmised that you would not be able to avoid giving them an undue preponderance." So while the tripos certainly gave them the motivation, the St. John's College Cambridge students were not the only ones diligently reading the journal. George Boole, for example, was altogether outside of the university sphere, Cambridge or otherwise. The Cambridge Mathematical Journal was admittedly primarily a venue for Cambridge mathematicians. In fact, 21 of the 26 identified contributors to the journal had a Cambridge affiliation. However, it also represented a means for the outsider Boole to get his work noticed by other mathematicians. Boole, though mathematically gifted, had not attended university and had taught from the age of 16 at various institutions in or near Lincoln. After contacting Gregory in 1839, he began publishing in the journal and thereby introduced himself to Cambridge mathematicians. Soon enough, Boole, too, was conducting research that involved the calculus of operations. Specifically, Boole attacked the problem of the solution of linear differential equations with constant coefficients, the same problem that Gregory had discussed in 1837 in his first journal article on the calculus of operations. This 1840 letter from Gregory to Boole indicates that the latter had tried to get this research published in the Philosophical Magazine to no avail. It also reveals Gregory's opinions about the existing publication environment for mathematics. Calling Boole's method exceedingly ingenious, Gregory wrote that, quote, "I do not think that the non-insertion of your paper in the Phil Mag was due to any other cause than this, that the editor is ignorant of mathematics and is very unwilling to risk the publication of any mathematical communication unless a previous knowledge of the author gives him some security for the correctness of the paper. So although the philosophical magazine was Boole's first choice and not the journal, and also as Boole's result seemed to be a great improvement over Gregory's, Gregory was still magnanimous, writing that, "I shall be very happy to get your article inserted in the journal." And he offered to draw up the paper in a way which I think is best fitted for publication. Now, the problem of differential equations with variable coefficients, whose difficulty Gregory had lamented back in 1837, had apparently not been very far from his mind. 3 years later, writing to Boole, he explained that, "I shall be glad to hear that you've made progress in the solution of equations with variable coefficients. The question is a very difficult one, and one of the highest importance, as it is in that direction that we must look for some extension of our means of analysis." Boole gladly accepted Gregory's offer to rewrite the paper, which appeared in the second volume of the journal. Boole soon successfully tackled the problem of differential equations with variable coefficients with the calculus of operations. He was, again, unsure where to publish this memoir and asked Gregory's advice. Gregory's response gives us one more contemporary appraisal of the publication sphere for research-level mathematics. Gregory wrote Boole that, "I have been prevented from answering your letter by a severe attack of illness from which I have not yet recovered. My advice certainly is that you should endeavor to get your paper printed by the Royal Society, both because you will thereby avoid considerable expense," because Boole had thought about just publishing it by himself, "and because a paper in the Philosophical Transactions is more likely to be known and read than one printed separately." He then explained that Boole would have to get a society member to communicate the article and offered to get Airy to do so if Boole couldn't find anyone else. Boole took Gregory's advice and submitted the paper to the Royal Society. It was not shelved on a dusty shelf of the archives. It was printed. And not only was it printed, but Boole received a royal medal for it in 1844. Koppelman has appraised this work of Boole's as his most important work in the calculus of operations. The breakthrough in Boole's memoir was his loosening of the requirement of commutativity among the operations. Boole emphasized in the paper that, quote, "The position which I am most anxious to establish is that any great advances in the higher analysis must be sought for by an increased attention to the laws of combinations of symbols. The value of this principle can scarcely be overrated." So in George Boole, then, we have an example of a mathematician totally outside of the university sphere, who made his publication debut and also gained some of his motivation in research-level mathematics in the Cambridge Mathematical Journal. The discussion in which he participated in the journal exposed him to a pressing research problem among young British mathematicians and pushed him towards ideas concerning laws of combination, ideas that he would later apply to his symbolic logic. As Gregory alluded to in his letter to Boole, by 1843, Gregory was in the midst of a recurring illness. He was first attacked by this sickness late in 1842, and by the following spring he'd left Cambridge, to which he would never return. The November 1843 number of the journal was the last issue that he would edit. Gregory finally succumbed to illness in 1844 at the age of 30. In his absence, the direction of the Cambridge Mathematical Journal was assumed by Robert Leslie Ellis. After editing the journal's 4th volume, Ellis sought someone with whom he could entrust his editorial duties. William Thomson, who would later become known as Lord Kelvin, agreed to Ellis's proposal and began a new series of the journal. Although Gregory had played such a vital role in its inception, the discussion in the journal on the calculus of operations did not die with him. Bryce Bronwyn, Arthur Curtis, Francis Newman, William Duncan, W.H.L. Russell, William Spottiswoode, Robert Carmichael, and William Center all published papers involving the calculus of operations in the new series of the journal called the Cambridge and Dublin Mathematical Journal. While these are certainly not all well-known or even known names in the history of mathematics, their activity in the journal still indicates to us that a constant mathematical discussion was taking place on the calculus of operations. The continued onslaught of these articles was enough to frustrate Thomson, who tried to promote applied mathematics in the journal. He wrote to his de facto co-editor and fellow applied mathematical sympathizer, George Gabriel Stokes, that I shall be very glad to get publishing your paper in the journal, as I am very desirous of getting such papers on physical subjects, sometimes in place of the endless algebra and combinations which so abound. Duncan Gregory created a platform for the publication of mathematics by young researchers. And in doing so, he fostered a discussion on the calculus of operations that would remain a research focus for British mathematicians throughout the first half of the 19th century. This discussion, in turn, exposed these mathematicians to ideas that helped turn their thoughts to the development of algebra. Thank you very much. Not so much in the modern sense that we know of. Pretty much Gregory was the kingpin. He read them and decided what was publishable or not. And I would say especially in the calculus of operations, because this was an area that he was very comfortable with. Now, when Thomson started editing the Cambridge and Dublin, he was more interested in applied mathematics, and these articles on the calculus of operations became increasingly foreign to him. So he would farm out the articles to his friends to referee.
I always puzzled by the very little reference to the work of Babbage in this group of people that published in the Cambridge Mathematical Journal. It's like a break from the 18, 14, 15 papers to the ones in the 30s.
It certainly is a break, and we could even see that Gregory forgot about Herschel in his first article, and only later even realized that Herschel had written anything on it. It was kind of a generation. I could just maybe speculate that there really did seem to be a generation gap there, not wanting to adopt the mathematics of the older folks at the school.
What about the reception of the operational calculus on the continent? You mentioned,
right.
From Lagrange inspiring some of the work of the British mathematicians. What do we know about
going the other way? The reception was not quite as good going the other way, especially during this time period. Only later in the 19th century, I think, did any sort of cross-pollination occur.
The only person I can think of is Hermann Hunke, but that's later. That's the end of the 60s, I guess,
mm-hmm.
70s. But he never quotes Duncan, as far as I remember. He quotes Peacock and some others. But.
Yes, I think there is one Italian article that was the 1850s or 1860s, and I have that reference, but that's all that comes to mind. Again, I think Niccolo Guicciardini argued that in adopting this Lagrangian and then the operational outlook, the British thought that they were cluing in to the continental century of improvement, and again they isolated themselves. But that's not necessarily a bad thing. It just spawned a different approach.
Can I ask a little question? When you solve a differential equation by whatever means, it's open to you to check the answer.
Right.
And given that they're worried about what rules apply, do they actually check the answer?
Yes, they do. And they so like I said, the utility was the biggest thing, not so much the legitimacy. At the end, they would say, and look, it worked. So they would check
on
it.
a pendulum, which is obviously a very important and applied question, that could have been accepted by someone designing clocks as a workable piece of mathematics. No more questions. I think we should slank. Thanks, Sloan, very much indeed.
Thank you.
Thank you.